In this video, we're talking about Hooke's Law, created by Robert Hooke, and we have a couple of years here. I saw some conflicting information about when it actually came out. So somewhere in the 1677 to 1679 range. This was actually the quick and dirty copyright that he came up with. He thought he had figured it out, but he needed to do more testing. So what he did is he took as the tension, so the force, translated it into Latin, and then basically wrote all the letters in alphabetical order, so that later on he could go, wait a second, I did it first because in 1677 I wrote that, and that translates to this, and that translates to that. So anyway, it's quick and dirty. I did it first. So Hooke's law basically is looking at the force is equal to negative times this stiffness constant or spring constant times the displacement from equilibrium. This force right here is the force that the elastic material exerts, not the force that I would require to move something. If I had something on a spring and I pulled it down, the force that Hooke's law is talking about is the force that the spring is exerting, not the force that I'm exerting. So what he's claiming here is that the force and the displacement from equilibrium is directly proportional. And if you plotted this, you would end up with that the slope, and that's the symbol I use for slope, is equal to that spring constant. Now, if I'm applying a force and seeing how far it stretches, then properly how far it stretches is dependent upon the force. And so this would be the graph that you would do, in which case the slope is 1 over the spring constant. Now, not every material will behave this way. Not everything is what some have referred to as a Hookean material, but it works for a great number of things. And as a note down here, rubber bands don't behave that way perfectly. So if I double the force, I double the stretch. So as the tension, so the force. So the way you would actually test it is you take a material and mark its natural length. So that would establish the equilibrium spot. You apply a known or easily calculated force. So when I say easily calculated, I can apply a mass, and I can find the weight of a mass relatively easily. Now, I'm not hooking a mass to a spring and just letting it go. I'm hooking it and then I'm lowering it gently so that the mass is still in equilibrium. I measure the length and then I plot. So then I do a couple of masses and a couple of different data points and I plot them. Now, there's 4 different ways of dealing with this. One, if I choose equilibrium to be 0, which is sort of the claim I made on the previous page, then my plot should look like that. If I set some other position as 0, then my plot will basically be this, but shifted up or down. Here, I'm assuming that my initial displacement is positive. So that might be, if I have a spring hanging down, then the point of where the spring is hooked to whatever's holding it up might be 0, in which case my graph would look like that. In either case, well, if we take a look at it, so F is equal to K delta X. I'm not worrying about the direction right now. That negative sign just means that the force is acting opposite the direction that it's being displaced. So if you go back to the original side, if I pull a spring down or put a mass on a spring and it hangs down, that the force is trying to pull it back up. If I push it up, then the spring is trying to push it back down. Spring or material, whatever it happens to be. So if ignoring the directions, so if F is K delta X, well, delta X is just X minus whatever your initial position is. And so we end up with this. Initial position is set, K is a constant, and so this whole term right here is a constant. So I add Kx naught to both sides, and then I just flip the order around. So Kx is equal to F plus Kx naught. X, solving for X, we end up with this equation right here and get it into slope-intercept form. That's the classic y equals mx plus b, or the way I write it, y is equal to slope x plus b form. That's as an x-axis, that's in the y-axis, the classic brainwash math way. And so my force is on the x-axis, my position is on the y-axis, and I guess I'm over on this one, force axis and y-axis. My intercept will be x sub naught, so that will be my initial position, and then 1 over k is the slope. So slope is equal to 1 over my spring constant. If I set equilibrium to be 0, then we end up with the exact same process that we went through before, it's just that x sub 0 is 0, so that this whole term drops out, and we end up with this, so I end up with my slope and intercept. If instead I do plot versus mass instead of force, then I have my position is equal to g over k m plus x sub naught, as in this situation right here, and now my slope is g over k. So my spring constant would be g divided by the slope. As over here, k is just equal to 1 over the slope. So it does matter how you are actually plotting it, whether it's versus mass or versus the force, which in the scenario I set up here is the weight of the object. And then if we assume equilibrium is 0, that my intercept becomes 0 again, but my slope is still the same as it was here. So that's the basics of Hooke's law. There are other videos out there which go into some more excruciating detail, or just enjoyable detail.